So the project I wanted to show you today was this one. This is the classic buffer overflow, which I keep talking about in the lecture, and I'm a security teacher for most of my classes, so I am focusing on the security aspect of this course. And so that's why a lot of these projects are related to hacking and security. But anyway, this one here in particular is the classic buffer overflow, and that's how I learned about how the stack works and all that by learning how to exploit it. So let me bring up the instructions here. And I have a Intel-based machine here that I've connected to with SSH. I'm on an Intel Mac here, so I don't need to have a simulated Intel environment, although I know some of you do have one, and I do have one on my other computer, which is a Mac M1. So here I am with, if I do uname -A, you'll see I in fact have an AMD 64 processor. So this is the processor expected for this, and that's what you need. You need an AMD processor for this project. Yeah, I think you do. Otherwise, the buffer overflow won't work. So the program we're going to exploit is this one. It's a very simple program. The main function is down here, and all it's going to do is call this function called test password. And the test password function is going to read a password from the person at the terminal, and it's going to read up to 50 characters from standard in and put it in a variable, but the variable only has room for 10. So there's a possibility of a buffer overflow here. Then it's always going to return 1, so this is always going to be true. It's always going to print fail. You will never make it to win. No possible value of that password will be accepted by this code, so you should never win. But we are going to figure out a magic password to feed in that's going to cause a buffer overflow and execute the win code. That's the goal here. So you compile this thing, and on my system, I preferred to use this compiling with the NoPy in it. That is determining whether it's going to be position independent executable, which will have a strange address and be more hard to work with. So I recommend doing that one. There are ways to tell which one you've got here, but you can tell with the file command. After compiling it, it's pwd32. And the file command here tells me it doesn't have pi. It's no pi. Pi is position independent executable. And if you have that, the addresses will be all full of zeros and hard to use. All right. So now we can run this program. Come on, I got to get there. /pw. There we are. I can run it. Ask me for a name. I give it a password. I give it 1. All right. But if I give it a long password, then I get a segmentation fault. So that shows there is an error of some kind caused by this. Now, I'd like to have address space layout randomization turned off, and I see that I already have turned it off on this machine, because this password address is always the same. If it was turned on, you would see a different number each time you run it like this. So if necessary, you execute these 3 commands to turn off address space layout randomization, so it stops moving the address around, and that makes it easier to exploit it. So we render the debugger in quiet mode for pwd32. And now that we're in, we can use source code debugging because I compiled it with the G switch. So I included the source code. So now you can see here's the routine that's going to have the buffer overflow. This fget_s command is where the buffer overflow happens, where it reads data from standard in and puts it in a password variable that's only 10 long. So I'm going to put a break at 9, so it will stop before executing line 9, after the overflow, but before it tries to return, I want to see what has happened with memory. So break 9. Now I'm going to run it, and I'm going to give it an AAAA. Something I know that's going to be 41 in hexadecimal for a password. Now it hits the breakpoint, and so I do info registers. At this point, the stack goes from 470 to 488 in the last few digits. So the stack is not very big, and so I can examine it with x12x ESP. And it goes from 470 to 488. This is the 4-byte word starting at 480. This is the one starting at 484, and this is the one starting at 488. So that is the stack frame. These are the local variables, and here you see the A's I typed in. A. A, capital A, is 41 in hexadecimal, so it's easy to spot. And here is the return pointer. So if I put in a longer string, I can overwrite the return pointer, and that's my goal. So I'm going to put in this one. So I run it again. Start from the beginning is fine. I put in that long password, and now I hit the breakpoint. Now I'm going to check the registers, and notice the stack is still going from 470 to 488. This is the fundamental problem with C. I put in a longer string, but it did not reserve any extra space to store it. A smarter program like a coding language like Python or Java would have automatically reserved more space, or Rust, but C does not. So it's going to try to jam that long password into space that was really only had room for 10. So if I look at the stack frame, it's no bigger than it ever was, ending here, and there's the return value, which now contains the value 46, 46, 47, 47, and this is 41, so it's 1, 2, 3, 4, 5, 6. That is 2 F's and 2 G's going in their variable. So if I continue, it's going to crash with this invalid address in the instruction pointer, and you can do info registers to see that. EIP now contains that ridiculous ASCII value, which is not valid for this program. So I now know how to do it. Take the last 2 F's and the last 2 G's. They're going to end up in the instruction pointer. I can put anything I want in there. If I put in something stupid like FFGG, I'll have a denial of service condition where I crash the program. What I want to do is win. So I disassemble the win function. S tab there, win. All right, so here's the win function at this address, 080491D4. I'll just put it in the clipboard. That's the address I want to put in there. So now I know what I'm doing. I can quit from here, and let's look at my exploit, which I've already got set up here. Here is the Python code that does the exploit. I feed in all of this string up to the first 2 F's. Then for the next 4 bytes, I put in my instruction pointer, and then I finish the length. And the value I want was this one, 080491D4. So I put those bytes in backwards because it's a little endian processor, so you put the low bytes first. So it's D4910408 to mean that address. So now I print this prefix, those 4 bytes for the EIP, and then the postfix just to make the total length of the input string the same, which is a good practice in exploit development, so you'll always hit the same line of code. Different inputs might cause different crashes, and when you're trying to improve an exploit and make it more powerful, you want to keep hitting the same weak spot every time so you can penetrate. So this should put that value in there. So if I run GDB -Q and get back in there, first I'm going to put this in a file. So I can run this program, exploit pwd2, because I've already shemoded it +X to make it executable. And so it prints out the stuff, but notice you don't see any of the characters here because they're non-printable. They just turned out to be non-printable values. So what you do, one way to handle that is you put the output in a file, which is what I did here. All right. And I got to have a dot at the start of it. I didn't copy there. That'll run the program and output redirect to put it in attack pwd32. And then you can use XXD to see the hexadecimal output. Now you can see, here's the FF. Here's the 4 unprintable characters after the FF D4910408. Those are the 4 bytes I inject, which are the address of the win function. So now I can GDB the program pwd32 and run with arguments, taking the data from attack pwd32. This is what we talked about in the lecture. This is input redirection. It's going to read from this file the data and feed it in as an argument. And now it's going to print you win and then have a segmentation fault. And if I want to see that in more detail, I can put a break 9 and then run it again. Probably just, this again, and say yes. All right, and now it's going to hit the breakpoint. Instead of going right through the attack, I can info registers and see that once again, ESP and EBP, this time it's 460 to 478. The absolute addresses have changed a little, but the relative hasn't. It's only saving me 18 in hex, which is 16 plus 8. 24 bytes is all it needs. So I can examine the stack. And here is the stack frame. And there's the return pointer, 080491D4. And if I disassemble Win, I'll see that address is this address, 080491D4. So when it tries to return from this function, it's going to go to Win instead. And if I just continue, it does print you win, and then it crashes because I didn't actually restore the base pointer and return correctly to the operating system. I did some collateral damage here that I didn't repair. So it isn't a clean exploit that prints you win and then exits cleanly. It prints you win and then crashes. But it did accomplish my goal of running this code which the developer did not want me to run. So that's the essential thing of a buffer overflow exploit. If you understand that, you understand essentially what's going on here, and there's a lot you can do for extra credit here. There's a couple of flags you do to show that you understand this, and then you can try 64-bit version. You can recompile the code with 64-bit addresses. Now you'll have RBP and RSP that are longer, and RIP for the instruction pointer, the base pointer, and stack pointer of the current stack frame, but all the same process is the same. Now the return pointer on the address is two words here. So this is 0x555547F1. That's the return pointer. Again, you overflow the stack. You find some characters there. You can make an exploit file that will go to the win function with the much longer address. You do the same thing in 64 bits. And then I was real pleased. I went to DEF CON China. I was in an airplane for like 14 hours, and I realized on the airplane that I could pre-program scripts on the server that run GDB. So you could exploit a real remote server with this kind of exploit, because it runs a GDB script that gives you the information you need. It runs a script that does these things, in fact. So here, I have a string processor running on one of my servers. You can just feed in a string like AAAA, and then run the debug, and this will show you first the source code. The source code has some flags, and I was able to redact it, so you can't see the flags here, but if you can run this code, you'll get the first flag, and if you can run that code, you'll get the second flag. All you can do is feed in the value, the input value though, and the input value is the product key here. That's what you're feeding in. So this is going to call a function called activate key. Here's the activate key. This is very much like the example I showed earlier. In here there's going to be an overflow. There's 25 characters reserved for this, but it's going to copy the string into it, however long it is, and it can be up to 100 characters. So this string copy can overflow the key variable, and now you can do things. If you can make the 30th character of the key 7, then you'll get the first flag. And if you can take over the instruction pointer and run the win function, you'll get the second flag. So here you have the address of win. This disassembles the first byte of win, so you know the address of the win flag. Here's info registers at the point of the crash. Here's ESP and EBP going to DC48. Here's the stack, so you can go down to FDC48, which is here. That's the stack frame. This is the return pointer. I put in AAA, and here it is AAA. So here's the data I put in for my short string, and so you can hit those product keys. And by the way, one thing that you'll have to start with is figuring out how to put non-printable characters in. You could write a Python exploit file, but you don't need to because it's right up here in the URL. So the way to do this, let me open a text editor window here and show you. The way I do this, you don't need a Python script or anything. You can just manipulate the URL. There's the URL to send the AAA. So let's send it some binary stuff. All you do is % and then hex code 01, %02, percent that should be. Okay. That's all you have to do. This is going to give me A's and then the binary hexadecimal 1, 2, 3, 4. So if I send it that data by just copying that and putting it here, then if I look on the stack, I'm going to have A, and here's the 0, 1, 0, 2, 0, 3, 0, 4. So to get the first flag, you just need to put in a whole bunch of 07s until you hit the 30th point. But to get the second flag, you're going to have to feed in just the right hexadecimal values to run this win function. So it should be pretty easy. You can do it. This is the 32-bit version. And if you go on here for extra credit, there's a 64-bit version down below. Let me get back to my, here we are. There's a 64-bit version here. And these are taking strings. Down here, I have a server with address space layout randomization turned on. So it moves randomly. You'll have to debug it and then run it separately. And you can, in here you can put in hex values. So if you put in AAAA, it's not going to read that as 4 ASCII A's. It's going to read that as 2 hexadecimal AA characters. So if you go down here and look at the stack, you're going to find AA on it somewhere. Let's see, ESP and EBP 908. So there's the stack frame. And expected to find the AA in there. Somehow I'm not seeing it. Let me try it again with more of them. I can put it up here. I'll put more A's. A. There, see what that does. Might make it easier to spot. Well, I have to pay more attention to this one. I'm not quite sure where it's going. I expected to see them down here, but it must be a little more complicated than that. Anyway, have to read this code and figure out what the deal is. It's gonna win. Okay. Anyway, that one there, it does take arbitrary hexadecimal input, so you can put in unprintable characters easily. Another way to do it. Anyway, there's a couple of, these are pretty difficult, but you can exploit my server and get a shell and find hidden flags on it. So try this stuff out. There's quite a bit of extra credit to be gotten there, and it's all good. You're learning how these buffer overflows work. So I'm going to stop this recording.